Somehow the last time I gave a talk in the theory seminar, somebody recorded me on their phone and posted it to YouTube.
Oh.
It's very weird. And I was not aware of it. It's like, I Googled on YouTube my name and suddenly I see this recording. It's like, okay.
Yeah, it might be good to ask permission for things like that.
It's okay. I don't think I said anything that was unacceptable. But nowadays with technology, I think we should record all the theory seminars and post them if people don't care. I think it's it's the advantage of the time, if you want to call it an advantage.
Yeah, there is a slight disadvantage of that. Disincentivizes people from showing up and watching in person.
Well, but they don't care if you record, right? It doesn't show them in the recording, right?
Oh no, but I mean, if they know that they can just watch the talk at a time that is not 10 a.m.
Yeah, that's true. 10 a.m. is brutal. I agree with that interpretation. Yeah, okay, let's try the chat box.
Indeed, it works.
Excellent. Okay.
If there are any questions in chat that you don't notice, do you want me to?
Yeah, definitely.
Draw your attention to it.
I would try to pay attention, but me being me.
Okay.
Okay. Okay.
All right. Well, it is now 10 o'clock, so you're welcome to start whenever.
Let's see how many people are showing up.
13 and growing.
Yeah, let's wait another 2 minutes.
Okay.
Oh, okay. Okay, here we go.
There appears to be a question in the chat.
Okay. Let me first kill this and kill this. Okay. Exactly. I just made the version so that when I copy the file from the tablet, from the computer to the tablet, I could verify it's a new version. The true version number should be, E or pi, some transcendental number. Okay, let me start. So this is going to be, this talk is going to be based on 3. Whoa, that was fast. Okay, let me try again. That's the problem with this. Oh, I see. Okay, sorry about that. Let's try again. So this is going to be based on 3 papers. They are essentially with a group of 3 people, well, 2 other people. So Kevin Buchin from TU Eindhoven and his student Danielle Ola. I believe that Danielle might have given the talk on the first paper in the theory seminar a year or two ago. I'm not completely sure. So the first paper appeared in Sausage. The second paper appeared this summer in ESA. And the third paper just got accepted to the complement of SODA. So only the best for this theory seminar. Okay, so introduction. So we're going to speak about graph or metric spaces that they define. So consider, for example, the clique, and all the edges have weight 1. So this is called the uniform metric on 11 points. And we're interested in building. The problem with the clique, of course, is that it's very good connectivity, but it has a lot of edges, right? So a natural question is, okay, I would like to find a sparse subgraph that preserve the distances, right? So the rules of the game is that I'm allowed to create any subgraph I want in the case of the clique, and the edges have to have this, if they have weights, they have to have the same weight as the original edges. And we would like this subgraph to be preserve distances. So in this case, this star subgraph is a 2-spanner, namely between any 2 points in the graph, the distance is either 1 or 2. And in fact, it's easy to convince yourself that you cannot do better. What do you mean you cannot do better? Any graph that is a 2-spanner for the clique must have, well, it can have n-1 edges, but if you want it to be better than a 2-spanner, then it has to have all the edges in the clique. So essentially 2 is the best you can do if you really want a proper subgraph. And the problem, of course, becomes harder if you have weights on the edges or some of the edges are missing, right? So the study of this family of subgraph is those graphs are called spanner. A T-spanner is a subgraph of the original graph, such that for every pair of vertices, the distances are, first, they are expansive. They're no shorter than the real distance. And this is just to make things easier because you can always scale up. And the distances in the spanner are at most T times the real distance. Okay. And this topic is very widely studied because it's very interesting. Because in real life, we always want a sparse graph. We're not interested in dense graph. And the problem is, there are a lot of parameters that you can optimize, right? Of course, you can optimize the distortion. There is a trade-off with the number of edges. How is the metric given to you? Is it given as a graph, or are you given only the distances? Do you care about the average degree of the vertices, maximum degree? Do you care about the diameter of the generated graph, the total weight, and so on? So there are really a huge amount of work on this topic. And I will discuss some of the basic results known in this field, because that would be kind of the starting point to some of the stuff I'm going to talk about. Okay, now the interesting question is, what happens if a vertex fails, right? So for example, this vertex fails and it falls down, right? Just think about a network, the graph representing a network, and this vertex is a router that just fails, right? So the clique doesn't care, right? The clique is still very well connected after if this node is gone, not a big deal. But the spanner is gone, right? We deleted the center of the star. It's gone. The spanner is now dead. And the question, of course, is what can you do, right? So people study this problem. This is the problem of how to build a spanner that can withstand some failure. And In particular, a natural thing to ask is what happens if you allow k failures of vertices? So there, of course, was a lot of work on this. This is called fault-tolerant spanners. And I'm not going to go into this sequence of papers. Things get pretty hairy if you really want to get the optimal parameters. But I would note that a k fault-tolerant spanners, the number of edges must be at least kn, right? And the reason is because if a vertex has degrees smaller than k, then you could just delete all its neighbors. And at that point, this vertex gets separated from the rest of the graph, and the game is over, right? And the graph is no longer k fault-tolerant, right? Because the distance of this vertex from the remaining graph is now infinity. So that's bad, right? In particular, this means that those constructions are not very interesting if k is large, right? So here we are considering the case of catastrophic failure, right? Now, catastrophic failures are rare, but they happen, right? We lived through one of them right now. In no way am I speaking about the current administration or the current president or the current handling of the COVID, just to make things clear. Okay, so this leads to the following definition. This is a reliable spanner, and it has to withstand a catastrophic failure, right? So we have a set B, which is the failure set, right? Which might be potentially quite large. In particular, it might be almost all the graph. It's quite allowed. And then the basic idea is that if you have a bad set, you have this attack. So of course, all the vertices in the bad set are gone. They're out of the game. But then you're going to have a collateral damage, right? There's going to be a region around them that loses its connectivity to its good connectivity. But hopefully this collateral damage is going to be relatively small. And the rest of the graph is still a happy spanner that spans as well as you want, right? So formally we would require, we have some parameter theta, and we require that the collateral damage region B plus, which contains B, the bad set, it's only 1 plus theta bigger than the original set. Okay, so this was inspired by a paper by Bosset et al., or Bosset et al., I'm not completely sure how to pronounce it. So they studied this problem in a slightly different regime of parameters. They had things like if k vertices are failing and we allow k square vertices to be in the collateral damage, how small of a spanner can we build, right? So it's a slightly different regime of parameters because we are asking for a much tighter bound on the collateral damage. But from our purposes, the important thing is that they showed an n-log-n lower bound on the number of edges required for such a spanner, even under our regime. Okay, so here is another illustration that tried to deliver the basic idea through. So we have the bad set, and we might have those two vertices that can route around the failure region. But the new route is much longer than the shortest route. So clearly this vertex is damaged. It's no longer get the spanning guarantee that it wants. But on the other hand, two vertices that are outside this damaged set can still route quite well. And one thing that is important, you still can use vertices that are in the damaged set, but not in the attack set. You can still use them for routing, right? And that's kind of critical at some level to get anything useful here. Okay, so results are known only for geometric settings. In particular, what we showed was that you can build in D dimensions such spanners where it's 1 plus epsilon spanner, which is kind of the best you can hope for. And the dependency on epsilon is exponentially the dimension, which of course you cannot avoid. and the dependency on theta is something like polynomial in theta, and then the bound is very strange. It's n log n and polylog to the 6, right, which is a bit strange. I should say that independently of us, Boss et al. In a different paper than the one I mentioned earlier, came out with a slightly weaker result, right? So this is a case
Sorry,
of...
a question.
Yeah.
So the model is you're assuming n points in d-dimensional space and it's a complete graph. The distance.
Oh yeah, I should have said that. Sorry, this is so standard that I didn't define it. So yes, so if I speak about Euclidean space setting or metric space setting, you're essentially assuming the clique setting where the distance on an edge is just the distance of the metric. So in Euclidean space, it's just the distance between the points. And this is a setting that people like because the number, the description of the input is linear, but you're implicitly describing a quadratic size graph. So it's good for that. Thanks for the question. So I should have said that explicitly. Okay, anyway, this independent result is a case of a log long and a weak late. And they're using kind of similar techniques, but definitely not identical techniques. Okay. And then we had a follow-up work. This is the second paper I mentioned, where we asked, okay, what happened if the spanner doesn't have to withstand an attack always, but it has to withstand attack with good probability or an expectation. So I will explain what I mean shortly. Let me just remind you that there is a lower bound of n log n. So the big challenge here was to break the log n. So you can get n log bound. That's what we showed. Now, what do I mean here by in expectation and so on? So now we are in an Oblivious model. And what do I mean by Oblivious model? We construct the spanner with a randomized algorithm, because otherwise it doesn't make sense. And the adversary chooses an attack set, but they don't know the graph itself, right? They can kind of look on the input and figure out where they think what the graph of the spanner is, but they don't see it. And then they choose an attack set, and then you get the damage set, right? The damage set are all the vertices that are no longer have good paths for them. And you can think about this damage set as being a random variable, right? So in expectation, we want this damage variable to be only theta fraction bigger than the attack set, or with high probability or good probability to be at most this much bigger. So it's, at some sense, it's disappointing that it's oblivious, but on the other hand, because of the lower bound, you cannot really get anything better. Okay. So the third version, which is what I wanted to talk about originally, but somehow I'm not going to talk about it too much, is the graph, is the metrics setting or the weighted graph setting. So I give you a graph, undirected, connected, of course. It has weights on the edges. And we look on the metric the graph induces. So the metric graph induces just for every pair of vertices, the shortest path between them in the graph. And we would like to build a robust spanner for this. I should say, by the way, that I'm still allowing every edge that I want to put into the spanner, even edges that are not in the original graph. If one restricts oneself to the edges of the graph, I know nothing, and I think it's an interesting problem. And this is exactly related to the question in the chat of whether we allow Steiner points. So we don't allow Steiner points, both in the metric space, in the Euclidean settings, and in the finite metrics space settings. In the Euclidean setting, it just doesn't help. You don't need it. And in the metric spaces, I That's a very good question. It might help. So that's another interesting question for further work. But if you allow Steiner points, you know, there would be good candidates for attack. So somehow it's not obvious that they would help. Okay. So the first case we study is the uniform metric. So that's just the clique I showed earlier, right? You have n vertices. The distance between any pair of vertices is 1. And we showed that you can do 2 distortion and it's reliable in expectation, and the number of edges have to be this. Linear times some function of this theta, the reliability, you know, the reliability parameter, how much expansions you want. And this construction is pretty simple. You can think about what it is. But then the bad news come. One can show a lower bound of n to the 1 plus 1 over t, where t is the distortion, which is kind of surprising. And we show an upper bound. The upper bound doesn't quite match. So we have, oops, sorry about that. Okay, I guess not. So, you know, we have an extra t parameter, which now believe we might be able to remove. And we have, of course, dependency on the reliability parameter, which we need to have. Okay, so that's the uniform metric, which should be the basic, easiest case to handle. And then you can extend it to finite metrics. You have to assume that the spread is polynomially bounded, because if it's not polynomially bounded, one can show an easy exponential point example showing that at least our approach would not work, although maybe there is a different approach that would work.
And, Ariel,
yeah.
Quick question. Can you go back to the previous thing?
Sure.
Yes.
Let me use this opportunity to delete.
I mean, I guess for distortion T, I mean, in some way, isn't that this kind of spanner lower bound in some ways?
Right, but you know, the first construction, the randomized construction, shows that you can do better, right? So for the uniform metric, you can have a spanner with n minus 1 edges and distortion 2.
Right, but here you see, I mean, you're not.
I'm using uniform metrics here. This is the very special case.
Yeah, I understand, but you see, the interesting case is when nu is a constant factor of the vertices, and then you're getting a huge thing. No, am I mistaken? Nu is what?
Well, it's theta, but
no, fine. No.
Yeah.
I mean, nu is the fractional number of vertices.
No, theta. No. So this is very important. The number of vertices can be anything.
Yeah, but what maybe I missed.
So theta is the expansion, right? So we have an attack of the vertices. This can be any subset. It can be half the vertices, right? And then we have the damage set, which is all the vertices that are no longer have good spanning, okay? And this set is smaller than this 1 plus theta. I would write it as nu, okay? So this is what this new parameter is, right? It's a parameter between 0 and 1. It's how much more damage is caused by the attack set, right? And the more theta is close to 0, you know, intuitively, the bigger the spanner has to be, right? Because the more edges you need so that you can contain the attack to a smaller set. You can contain the damage.
I see. Okay.
Make sense?
Yes, sort of, yeah.
It's all a bit weird. I have to agree. You have to kind of get used to this idea, but somehow that's the only way to go because.
Ariel, one more question on the model.
Yeah, let me go back to the thing that maybe demonstrated. Right. you know, since we're allowing any size of attack, that's the only thing we can do if we want. We just don't want to take all the edges, all the quadratic number of edges in the metric, right? So if you want to contain the, you know, the important thing here is the definition, the model, that you're allowed to say, okay, we are allowed to sacrifice some bystanders, and the remainder has to be good.
Right. So one question here. So when you say G minus B is a T spanner for V minus B plus, so you remove B and you look, no, you remove B plus and you look at the distance,
no, you remove
the original
B,
graph.
not B plus. You remove B. So
Okay.
the red set here, this is B, this is gone. Okay.
Okay. And you look at the
you're
distance.
still allowed to go to this set B plus, although, you know, those vertices no longer have good spanning, right? This vertex cannot go to this vertex with a good path, but it still can serve other vertices paths to get a good path.
Right, but when you're trying to approximate distances, are you looking at the distance after removing B in the original graph?
No, so that would be a natural thing to do, in fact, but no, we are looking on the original distances.
I see. So you're trying to approximate the original distance even if B fails.
Right, but I'm approximating it for only the things outside the damage set.
Okay.
So let's go back to our usual broadcasts. No, it wasn't that fast. Okay, so then you can get other results. The other is the result for the finite metric spaces, and the other different metrics follows by a kind of a plug-in reduction, which I would talk about it towards the end. But the nice thing is that you can get pretty good results. Maybe I should say quickly what are ultrametrics. So ultrametrics are just trees where the points are leaves of the tree. Every internal node has a label, which is the diameter of this subtree. And for every 2 points, the distance is, you look on the least common ancestor, the label written there is their distance. And ultrametrics are simpler than trees, slightly simpler than trees. And there was a lot of work into, this is the Bartal result of embedding general metrics into ultrametrics. It's a very nice, powerful tool, so that's why people care about it. And we also get results for planar graphs and so on. And notice that again, we have the dichotomy we had before, where in expectation, you get essentially linear time, near linear number of edges in the graph if you are allowed an expectation. But if you want to get the real thing that can withstand any attack, then you get this pretty unexciting bound, and the distortion also is pretty bad, right? It depends on T, and T can be quite large. And as Chandra hinted, this is related to spanners. Results we know about spanners, more about that in a bit. Okay, so let me tell you a little bit more on spanners. This is kind of intended to educate people that don't know about spanners. The standard algorithm for spanners, let me just so the standard algorithm for spanner is, to constructing spanner is the greedy algorithm. So it's a very cute extension of the Kruskal algorithm. So I give you a graph with weight on the edges, and you sort the edges by weight, and you start adding them, right? And the name of the game is that whenever you consider an edge, let's call this UV, that was supposed to be U. I guess it wasn't U. Okay, so whenever you consider an edge UV, what you do, you check its distance in the graph compared to its distance in the current spanner you built so far. If this distance is too large, right? Formally, if it's bigger, the distance in the current spanner is a factor of 2k minus 1 bigger than the true distance, then you put it into the spanner. So it's a very simple algorithm. You can think about it as MST, right? Kruskal does the same thing, except that instead of 2k minus 1, you have, you can think about it as n. Are they connected? Or infinity if you want, right? If they are disconnected in Kruskal, you add them, right? So it's a really cool extension. And then the analysis of this algorithm follows using the observation that you never get a cycle here that have length with more than with less than 2k edges, because if there was a cycle with 2k edges, look on the last edge being added. This edge that is being added is the longest because we add them by length. So this is the longest edge. There are 2k minus 1 edges that are same length or shorter, so it wouldn't pass the test of adding it. So this graph, all the cycles must be large, right? This is called the geert, the smallest cycle in the graph. It must be of size at least 2k plus 1. And it's not hard to see that this graph, the number of edges is n to the 1 plus 1 over k. And the proof is easy. You repeatedly remove all the vertices that have this degree, and either you're done, there are no vertices left in the graph, so then we are done. Otherwise, the vertices you're left with are all very high degree, and then you just take one of the vertices, you do a BFS, and the BFS can have depth at most k, because all the vertices at degree are high degree, but then we get a cycle of length 2k. So that's a contradiction. So that's kind of the nice basic result about spanners. And this is related to Erdős-Geert conjecture. So Erdős conjecture that there is a graph where the geert is 2k plus 1, and the number of edges is what we had before, n plus 1 plus k. So if Erdős-Geert conjecture is correct, then the construction we had is optimal. What one can show with a bit of work using random construction is that there is a graph with this number of edges, which is smaller, which with the geert being 2k plus 1. And essentially what you do, you just pick every edge with the right, you look on all possible edges, you pick every edge with this probability, and then you look on the expected number of bed cycle you get. You upper bound the expected number, and this number is smaller. This number is smaller than the number of this threshold that I wrote here. So you can just delete an edge from every bed cycle, and you get this lower bound. And I'm not completely sure, but I believe that this is currently the gap on this problem. So this is one of those problems where the gap is huge, and although the problem is important, no progress really was made on this, as far as I know, except for a lot of special cases, of course. Okay, in either case, if Erdős conjecture is correct, then the spanner thing is optimal, because look on an edge that is on a cycle in this graph. So because the cycle must have edge, at least 2k plus 1 edges, any cycle that contains this edge, and currently the distance between those two vertices of the endpoint of this edge is 1, but once I remove the edge, the distance becomes 2k, which means that a 2k minus 1 spanner must include this edge, right? So, which means that all the edges of this graph must be in the spanner of this graph. So we get that this the greedy algorithm is probably optimal. It's believed that this conjecture is correct, for what it's worth. Okay, let's see how much time I have. Okay, so let me tell you about the one-dimensional problem, because already the one-dimensional problem is very cute. So I give you numbers, 1 to n. Those are the points along the line. And for every 2 point I and j, the distance between them is just the difference. And Of course, a spanner in this case is trivial. You just connect two consecutive numbers. So you cannot do any better than that. So n-1 edges, we are very happy. But the question is how to make it reliable. And it's completely not obvious how to do that. And maybe if you thought about the original definition, the original definition of the problem with this damage set and so on smells a lot like expanders. And indeed, the expanders just have entered the game. So a quick reminder, what is an expander? Expander is a graph.
Can we go back one slide? So for reliability, so can we quickly see why this obvious spanner is not reliable?
Yeah, because I can just delete this vertex, right? All the vertices, sorry, I should have said that. All the vertices on the left are now disconnected from all the vertices on the right, right?
Oh, so you're not on the metric space, okay.
Right, well, no, so, okay. We are in the metric space as far as distances, but the spanner, this is in fact a good point. The spanner, we are using the shortest path metric of the spanner. Right, so the input is given us to as a metric space, but we build a spanner and now we care about the shortest path distance defined by the spanner.
Right, okay.
Yeah, so yeah, I should have said that. Okay, so and in particular, okay, so maybe I should say something about this, right? So it's easy to say, oh, well, just do 2 jumps, right? Add 2 jumps to the graph, right? And so on and so forth, but somehow this is not enough. Okay, so a quick reminder what expanders are. So for every subset of the vertices, usually you require that the subset is not too large, so at most half the vertices. You require that the number of neighbors of this set of vertices is large, let's say 3/2 times the size of the original set. The constant here, you can change it. It depends on the, it's one of the parameters of the expanders. There's, of course, as hopefully you all know, there is huge literature on that. The random construction are very easy, but by now we have several explicit construction. They're more complicated, but by now, some of them are simple enough that they can be understood, at least why they're correct, not necessarily the intuition.
Cyril,
Okay.
one thing may be helpful for people to see, right? Why maybe expanders come in and things like that. Right?
It would show up in 2 slides.
Yeah, right. So that even before thinking about shortest paths, even connectivity is important, right? So
yeah, that's literally the thinking below.
Yeah, I mean, when you define the problem, is forget first spanners, preserving even shortest path distances, even preserving whether 2 things connected, right?
Right, exactly. So as Chandra just said, expanders have the nice property that if you delete it, this is well known. It requires some work to prove it formally, but especially with the strange way reliability is defined. But it's well known that if you take a set of vertices, remove it from an expander, what remains is connected. Formally, what's known is that there is a huge connected component that connects almost everything. And what this connected component has diameter log n, like the original expander. And there are only tiny islands outside this huge connected component. Essentially, exactly the same definition of damage set, right? So you get connectivity, reliable connectivity, but it's a bad spanner, especially if you just want log n connectivity. If you want distortion better than log n, it's a bad spanner. But that's why really expanders enter the game, because expanders are unstoppable, right? That's really what the definition says. Because if you build a set that that try to block them, right? This bad set, somehow any set that you take, because it's going to go to a much bigger set, it expands, it would overwhelm the bad set. That's the intuition. And the bad set somehow can only damage things that are really close to it, and somehow you're very unlucky and all the edges go into the bad set. And it can happen, but it can happen only very locally and for very few vertices. Okay, so this is why expanders entered the game. I hope that makes it clearer. Okay, we need are there other questions? Okay. So we need a specific version of expander that is bipartite. So this is a pretty standard lemma. It follows immediately from the probabilistic method. So you have two sides. They don't have to be equal size, but conceptually think about them as being equal size. And now what we have is that you have if you have a subset on the left, which is sufficiently large, so it has to be larger than Xi, the size of this left side, then it's connected to everything, almost everything on the right side. Right. So the neighbor on the right side are almost everything. 1 minus Xi of everything on the right side. And as I said, this follows immediately from the probabilistic method. It's not hard. You get n over Xi squared number of edges. So we need this. This would be our building block. And the basic intuition is that, okay, expander is really good with connectivity. The regular expander is really good with connectivity, but it has bad diameter, log n, right? Bipartite expander in some sense are better in the sense that we know how to connect the left side and the right side by one edge, right? For every vertex that are still connected, it's going to be one edge, so we can control the distances. So those are better than our for our argument, but now we need to somehow connect everything up using those bipartite expanders. So that's the plan of attack. And the basic idea of the construction is now we take the points, we build a balanced binary tree on the points. Just think about the number of points being a power of 2. For every vertex now, we have an interval that it corresponds to, right? And we're going to call this interval a block. So we're going to get every node in the tree defines a block, and we're going to look on consecutive blocks. Right? So 2 blocks are consecutive, they're in the same level of the tree and they're next to each other. And what we're going to do, we're just going to build an expander, this bipartite expander between any two neighboring blocks. Okay, so every level of the tree, the total size, every block participates in 2 expanders. Expanders have linear size, so the total number of edges in the expanders built for every level is O of n, ignoring the dependency on the parameter theta. So overall, this is going to be n log n. So this is the size of the graph. Of course, what remains to be seen is why this construction worked. And I should also say something that I didn't speak about the distortion here. So here, we're going for the best possible thing, right? We are asking to construct a spanner such that the distances are exactly the same distances as originally are, right? So it's a one spanner. So what do I mean by that? I mean by that if you look on 2 vertices, right? And this is I, this is j, the distance is I minus j. So the distance in the expanders have to be also I minus j exactly. Now here, I didn't specify what do I do with the expander, right? So the idea is that whenever I connect 2 vertices, let's assume I decide to connect this vertex with this vertex, the edge that connects them, the way that I set it is exactly their distance, right? So if I require that in the resulting spanner, for every pair of points that the spanner still work for it, for the distance is I to j, what it really means is that the path between them must be a straight path. You must go from left to right. You cannot jump back and forth, because if you jump back and forth, the distance would not be good enough, right? If I do something like that, then this will be bigger. Okay, so it's in fact a pretty powerful requirement in this case. It's one dimension, that's why we can achieve it. It's essentially a spanner with no distortion. We cannot achieve it in any other settings. Okay, So that's the construction. Of course, the question is why it's correct. And the intuition comes from this idea of shadow, right? So what is a shadow? We are going to look on the points on the line, and we are going to mark the points that are in the attack set, right? So those are the red points. And now I'm going to build a curve. I start on the left. Every time I go to an attack point, I go up by 1. If a point is not in the attack set, I go straight, right? So I get this polygonal curve that goes up, right? Think about it as climbing a mountain, okay? And now the basic idea is, the shadow is that if you're on a point and you look on your horizon, you go to the right and you look to the right and you look on your horizon, and the question is, what's the angle that you have to look to the horizon? And the basic idea is that if you're just the next your attack point yourself, then the horizon is going to be 45 degrees, right? On the other hand, if you're far from the attack set, there are not many many attack points close to you, right? And there are also not a huge number of attacks that far from you, right? You're kind of if you think really of a shadow in a mountain, you're kind of in the shallow shadow. You almost can see the sun, okay? You see something. Then if you're shallow, then you have a hope to avoid the bad set, right? You can somehow, there are not too many things close to you, and you should be able to somehow hop over them, because you can create a coalition together with the other shallow points around you and jump. So that's the basic intuition. Let's see how I do it. Okay. Okay, so that's the basic intuition. And the proof itself, what it does, you look on 2 points and that are outside the damage set. So what do we define a damage set? So a damage set is a node, it's a block, such that the percentage of bad points in it is too large, right? So if a block is bad, we just remove it, right? This is going to be the damage set. And we are also going to remove all points that are in the deep shadow, right? So somehow we have points that are only in the shallow shadow, or not in the shadow at all, almost. And now we have 2 such points, and we want to show that they are connected by this graph. And the idea is that we're going to look on the path in the tree connecting them, and intuitively they're going to try and connect to their to go up to the least common ancestor. So the way they do it is that they try to go from their current node to their parent, right? So if they go to the parent, then the parent have 2 children. Let's assume that we are coming from the left child, right? So we have a left child, and we want to go to the parent. There is a right child, and the left child and the right child are connected by an expander. So if both the left child and the right child, are not in the damage set, it means that the percentage of bad vertices in them is small, which means that if the left side has a lot of good vertices that we can connect to from the original vertex, then the expansion property would imply that the right side also have a lot of good vertices, right? So as such, we can go, when we climb to the parent, we can use the expander of the right child to conclude that the block of the parent has a lot of reachable nodes. And we continue in this fashion. The only thing is that because of the left, because we allow only to move left, things are a bit more complicated. So we don't stick with the subtree. Sometimes we connect to the next node in the next subtree, but as long as we stay in the level, it's fine, right? Okay. So we do this on both sides simultaneously. We continue with this climbing up, always keeping the invariant that the current blocks are, have a large fraction of vertices that are reachable by a good path. until we get to the point where both the path that try to reach from the left and the path that try to reach from the right have two blocks of the same level that are consecutive. And then we are done because there is an expander between the left block and the right block. And as such, this is connected. Right? So that's the proof. Now, why does it work? Well, the idea is that none of those blue blocks or green blocks can be damaged, because if they would be damaged, then because those blocks grow exponentially, in fact, all those vertices would have to be in the shadow, right? Again, there are some parameters going on, but that's the intuition of what's going on. So that's why this, this construction works. Okay, so the result is that we get a graph with n log n edges that is a one spanner in one dimension. And as I mentioned, there is already a known lower bound, so this is the best we can hope for. Okay. Now, one can also do the Oblivious model, right? And the reason to do the Oblivious model in one dimension is because we want to avoid the log n. So what you do there, you do something very similar to skip list. So every vertex is going to be connected to a certain number of vertices before it and after it. This bizarre number is written here. So every vertex is connected to this certain number, and then you promote half the vertices to the next level, you know, by just randomly choosing them. And if you do that and you keep doing it all the way going up, what's a bit weird here is that as you go up in the levels, you connect every vertex to more vertices on the left and the right side. The intuition is that your number of vertices shrunk, so you have a bigger budget to connect things. So as you go up in the skip list structure, the higher lists have better connectivity. And one can show that this indeed works, and you get a linear number of edges instead of n log n. So this is for the Oblivious case. Okay. And the intuition is what I just mentioned before, right? Similar to people, shallow points are surrounded by shallow points, and as such, they can escape their locality to be connected to things that are outside the damage set. Okay. Okay, so I'm afraid I would have only time to tell you about the constant dimension. Well, let's see. I'm not going to have time to cover too much, but hopefully I can cover a little bit. So the extension to constant dimension relies on the idea that if you're in constant dimensions and you care about distances approximately, I had a recent result with Timothy and Mitch that showed that there is a constant number of orders that capture distances approximately. The number of orders depends on this approximation parameter. And essentially all you have to do is to plug in the one-dimensional construction into each one of those orderings. There are a lot of low-level technical details, and you know, nothing is easy, but that's the high-level idea. Let me skip the details because I want to tell you a little bit more about the other stuff. Okay, and the same thing works also in the Oblivious setting. Okay, let's speak a little bit about the uniform metrics. Right, okay. So the Oblivious construction is very simple. You just randomly pick vertexes. So here, again, we have a clique of length 1 on all the edges. So all the distance between any pair of vertices is 1. So the Oblivious model is you just randomly pick vertices and you create a star to them. Right? And, and this can withstand the Oblivious attack, because if the attacker did not choose one of the centers of the stars, then you have a two-spanner for everything else. So that's the Oblivious case. The non-Oblivious case is much harder. So here's the lower bound. I don't have time to go through the proof, so let me just sketch the idea. We claim here that any Oblivious, any deterministic reliable spanner must have a large number of edges. And the basic idea is that you look on the vertices. Either it has a lot of vertices that have degree n to the 1 over t, either it has a large number of such vertices, and then the number of edges is large, or the number of such, in fact, the attack is going to be all those vertices, right? We're going to just choose all the vertices that they have this degree or higher. So if there is a large number of such vertices, we are done because the graph has a large number of edges. Otherwise, what remains after this attack is only a graph with low degree vertices, but then it's easy to argue that there must be vertices that are not connected. In fact, most of the vertices are not well connected somehow. Okay, so that's that. Unfortunately, I don't have time to go to the detail more carefully. Right. Okay, and you can create a construction for the uniform metric based on this idea that you break the graph into clusters of the right number. And now from you just build the same tree we had before, but now we build this tree such that it would have, let's say, height t, okay, or whatever it is. And so it's a high degree tree, right? Every node has, let's say, n to the 1 over t children. And then what you do for every node, it looks like this. You have a cluster and subclusters, and every pair of subcluster, you just build this bipartite expander that we shown before. And then using a very similar argument, one can show that this is roughly a T expander with this number of edges up to some parameter matching essentially the lower bound. Right? So that's the upper bound. Okay, the final part, which I have only time to sketch, but maybe that's the interesting part in the last paper. So the basic idea is that we have a metric space and we want to cover it with uniform metrics because we know how to handle uniform metrics. So the basic idea is that we would like to cover it with a few uniform metrics, and then for every uniform metrics, we would know how to build the reliable spanner. So what is a cover? A cover is we take the metric space, we cover, we take a subset S of the vertices, and we set the distance between any pair of vertices in the set S. You can think about it as setting the diameter of the set, right? And we take a cover is just a collection of such clusters such that every pair of vertices in the set are covered by one of our sets, okay? And we have the property that the distance between those 2 points P and Q we care about is not much shorter than the diameter, right? It's the diameter divided by T. And of course, it's shorter than the diameter because everything is 2 pairs in diameters. But the important thing is that they require this for any pair of points in the set. So this looks very much like partitions, metric partition, which of course are very common. But the important thing is that we can do better than metric partitions. So we can get covers that are, for example, for planar graph, which are constant, have constant distortion, while if you do partitions, you need to pay something like square root log n. So this is a definition I have not encountered before. It's very natural. It's somewhat similar to well-separated pairs decomposition in Euclidean space. And using those covers, we can intuitively get all the results I mentioned before, because as I said, intuitively, you just cover every one of the clusters in the cover by the construction for uniform metric, and you take the union, and that's going to be your reliable spanner. And of course, I don't have time to go into more details. We had come to the end of this talk. All bad things come to an end, and all good things too. So I think the most interesting question, so I think there are two questions that are interesting. For me, the most interesting question is this reliability, because I don't think in algorithm, we did a very good, we didn't study very well algorithms and systems that can withstand catastrophic failures, right? We have very little on such setting, and in fact, algorithms are famous for being very brittle, right? So I think it would be nice to find other domains where one can consider a model like that. And I think here the question, if you move to a different domain, is to come up with the right question, right? You have to come up with the right definition. Here, the reliability is the right definition. For other cases, it might be, I don't know what it is. If I knew, I would have already worked on it. Now, in the domain of this specific question, what can be done if I restrict you to use the edges of the graph? So probably this question is much harder, but there is some recent technology that suggests at least that there is hope, right? People now know how to efficiently compute connected component or subgraph of a graph that are good expanders and so on. And you probably need to use something along those lines to get something for general graph. Even here, the question is not completely well defined, but I think it should be interesting. It's very clear that one would need to use much more sophisticated tools than the one we used. And I think, of course, that is also some interesting question in high dimension Euclidean space, because for there we know slightly better spanners than for general metric spaces. So maybe something can be done there. And that might be quite doable. I did not think about it too much. Okay, that's it. Thank you very much. Questions? Anybody there?
Yep, we're still here. Thank you very much, Sariel. Any questions?
Okay, all 3 papers are available from my webpage on the archive, and let me know if you have any questions, and bye-bye.
Thank you, Ken Sariel. And next week we'll have Sagnik Mukhopadhyay visiting to talk about his Stock 2020 result with Danapong Nanongkai. Thank you, everyone.
Okay.